Okay, so this chapter encompasses both work and energy, and let's start off with what you already know about work from your what do you know. What do you know about work? Work is what it takes to exert a force on something and cause displacement. Work is something you put in to obtain a certain output. Don't know. Action put into doing something that requires energy measured in joules. Unit is joules. Something about efficiency? Yes. You probably did efficiency in physical science? Yes. You did mechanical advantage, probably, things like that. Okay. It's the action of applying force. Objects do work in science. Work takes energy to create an output. The amount of energy necessary varies depending on the situation. And more horsepower! Watts. That's actually power, not work. Power is the rate at which work is done. Okay, what do you know about energy? Energy is required for work. Energy is what's released while work is a process. There are two kinds of energy. That's true, kinetic and potential. Actually, there's more than that, but those are the two that we deal with the most. Energy is what gives things the power to do work. Yes, but be careful about the word power because, again, in science, power is how fast you do work. It can't be destroyed or created. It can be transferred. That's true. Energy is the amount of work that you put into an object. It's the power to apply force. Objects have energy. Energy is either potential or kinetic. Movement versus stored, required to perform work. E equals mc squared. Joules and calories. Yeah, interestingly enough, energy and work are measured in the same units. They're both measured in joules, which points to a deeper underlying truth. What do you know about potential and kinetic energy? Are there different forms of each? We'll actually save that because we're going to start talking about energy and calculating energy and potential energy next week. So, let's finish up with your comments on this. And I did a good job this time blanking out the names. So, work is the amount and type of energy exerted to cause a change or a reaction. Many types of work, and it requires energy. Work is the human addition. Okay. Energy is the amount of potential capability or acting capability of any matter. Energy can't be created or destroyed. That's true. Measured in watts and joules is used to power everything we do. And of course, we just said energy is measured in joules. So leave the watts aside. We're going to get to that. That's power. Energy is the fuel to complete motions and reactions. Many different kinds of energy. I don't think they meant throws, but okay. All right, so you have some good information. I'm going to give you an even simpler definition for energy when we get there. But work is the force applied times the distance it's applied over. If you don't move something, no work is done. I can push on this desk from now until the cows come home, until I turn blue in the face, until I fall over. If I don't move it, I'm not doing any work. I'm exerting force, but as long as I don't move it a single, centimeter, no work has been done. Forces are balanced. No work is done. Work is equal to FD, and D is just like delta X. It's just distance. In work calculations, we typically use D instead of delta X. So that's pretty easy to understand, Samantha pushes on a wall for 3 hours, exerting 110 newtons of force. How much work has she done? None, but she's lost 3 hours of her life, which she will never get back. Existential physics problems. Okay. The catch comes in, and you remember all the problems we did in forces where we aren't applying the force on exactly the same axis as we want to move the object. If you think back to your, this is a box of my favorite things on a string, you were pulling at different angles. You can pull or push something at an angle that is not directly in line with the motion you're hoping to achieve. If you've ever pushed a car out of a snowbank, you know that you want to get as much of the force heading, straight along the axis of the road, or the parking lot or the driveway, as you can. You know, if you're pushing down, you're wasting a lot of force. So when applied force is in a different direction, the work is only equal to the piece of the force which is parallel to the displacement. That sounds really awful when we say it. It's not awful at all. Your book gives you this: work equals FD cosine theta. And I've seen numerous sources that say this. I get nervous about anything. This is just me. This is science and skepticism. Anytime they say, it's always blank, I go, oh, there's probably an exception somewhere. So your book gives work equals force times distance times cosine of theta, where theta is the angle. Theta is the angle at which the force is being applied. I hedge my bets, and I look at that force vector, and I break it up, and I see which piece is parallel to the displacement of the object. So, again, like when we did force vectors, can I use this angle or this angle? Sure, you can use this angle or you can use its complement. But if you're using its complement, obviously your trig functions are going to be different. So this is why I hedge my bets and I say, draw your picture, look at the picture, look at where the components of force are, and use the component of force that is parallel to the displacement, that's on the same axis as the displacement. Okay, I think this joke is dated because nobody gets it anymore. Okay, I've got one who's got a wry grin in the back. Okay, thanks, Zach. Zach, I think you and I have a lot of the same sense of humor, which, yeah, so network. When you have a whole bunch of forces acting on an object, and this is just like all the problems you did where 4 friends are pulling on a turkey, 3 friends are pushing on a car, 5 friends are pushing on a wheeled plant, okay, it's the same thing. When you got a bunch of forces acting on an object, to find the work that's being done on it, you have to find the net force. So this goes back to net force problems, and again, these are not difficult, they're just pains in the tuchus because they're nitty-gritty, detaily. So then we do the net work by finding net force. And again, once we find the net force, we have to look at the angle between that net force and the displacement. So to give you a numberless example, let me make that a smaller object. So if I have this object, okay, and I have 3 forces acting on it. Let me shrink that up. And I find, mathematically, that my net force is, I'm going to guess, somewhere there. Okay. I have my net force. What do we know about acceleration and net force? Well, think back to your equation for net acceleration. F equals ma. So if F net equals ma net, where is this thing going to accelerate? At the exact same heading as the net force. And you did a lot of these problems in Chapter 4. This thing, and I'll use a blue line to show how this thing is accelerating. Its acceleration is going to be exactly parallel. It's going to be on the line of that net force. So where is the work being done? With the net force. Okay? That's fairly straightforward, I think. And now we're going to dive right into the practice problems. 5A is on 169. So if you want to grab a book, open it up. We'll do the sample problem together, and then I'll assign the practice problems in the book. Okay, so we're asked how much work is done on a vacuum cleaner pulled 3 meters by a force of 50 newtons at an angle of 30 degrees above the horizontal. So just like we've always done, start off with an image, and we know that we have, oops, I guess I didn't really change that much. F applied is equal to 50.0 newtons, and this is 30 degrees above the horizontal. That's a terrible... Yes, ma'am. The question was, does it matter which direction it's pulling in? It probably doesn't, just kind of like our hills and slopes and ramps. But yeah, let's go ahead and sort of default to pulling in what looks to us like a positive direction. Force applied, 50.0 newtons. So what we want to know is how much work was done. And we're told that it moved, our delta x is 3.0 meters. Okay, notice on this arrow with the motion that you have to be really careful, because now you know how to do force arrows. Don't do a motion arrow connected to the object. Make sure that it's clear to you when you go back to it that that's not motion. Okay, so work equals force times delta x. Well, force applied, and we can see that there's a force applied on the x, a force applied on the y, and this thing's moving on the x-axis. So it's going to be equal to force applied x times the distance it was moved, or delta x. And force applied x here will be our cosine. So work equals force applied cosine theta times delta x. Nope, I'm wrong. You should use D. You know why? Because we are talking about distance, not displacement. What's the difference? Well, displacement, what is it? Displacement is just the difference between your start and end point. So if you push this thing from here all around here, but you end up here, your displacement is only this. But you've done all this work, because that's the distance that you moved it. You were applying force for that entire time. So yeah, I am wrong, and your book is right. You should use D, because it's the distance, not the displacement, not the change in position. Okay, so force applied is 50.0 newtons times cosine 30 times 3.0 meters. What is our raw answer? Okay, so our work is equal to 129.9030381006 joules. Yes, ma'am.
To avoid like calculator error, does it matter what the cosine theta is paired with? Can we multiply them all separate?
Yeah, you can multiply them all separate. Yeah, yeah. And on entering with these calculators, what I find is if you're not entering them all separately, you have to do cosine 30, close parentheses, put in the multiplication sign, and then put in your 50, and then put in your 3. But yeah, you can certainly compute them all separately. And if you keep running into issues with the calculator, I would do that. I was resistant to these calculators at first. I now love them. But I'd say it took me a good 4 years to not continually have calculator errors when entering strings in here. So yeah, absolutely. And how many sig figs do we have? 2. So the work here would be 130 joules. Let's really quickly look at the dimensional analysis for joules and what a joule is. Joule is obviously a derived unit, and it's made up. Let's do this. So work equals force times, times distance. Well, this is 1 joule times 1 newton times 1 meter. Okay. So a joule is a newton meter. What's a newton? So kilogram meter per second squared, because if we remember, F equals ma, so this is 1 Newton equals 1 kilogram times 1 meter per second squared, so 1 Newton equals a kilogram meter over second squared. So now we can put this all in. We have kilogram times, times meter over second squared times 1 meter. So 1 joule is actually 1 kilogram meter squared over second squared. So if you get into a rearrangement and you want to check yourself dimensionally, you have the tools to do so. And it's nice because at this point you can back this all the way out, because you know this at 2 in the morning, woken from a dead sleep with no coffee. Like, you could probably spit out the breakdown on what a Newton is. Okay? Assigned are all of the 5A practice problems. Okay, so assigned, page 170, 5A, 1 through 4. And we will not be doing worksheets in Chapter 5. We're just doing the book problems, which keeps it a lot simpler. Okay, there's no slide dedicated to this, but we're going to, especially when we start talking a little bit more about kinetic energy and how it's related to work, we're going to have to look at the sign on work. So if this object, and this kind of came up with the vacuum cleaner, and oh hey, can we make the arrow pointing this way so it's Cartesian positive, please, because it makes my brain not do somersaults and flips. So if we're pushing or pulling something that way, and it's moving that way, and its velocity is increasing, it's going from rest to motion, we would say that work is positive, right? Everything there lines up as positive. So the force that's being applied is positive, the distance that it's being moved is positive, the work is positive. Now, okay, this is really easy. This is always where the pitfall comes in. What if instead of the force on it, so let's say that the force on it is in what we're calling a negative direction, but it's still, and it's moving in a negative direction, and it's going from rest, it's being moved in that direction. So at that point, we have what kind of work? We have positive work, which is terrible, because work equals FD. This is negative, this is negative. That's not too bad. What if I make it worse? So what if we have something that is having a force exerted on it like this, but it was moving like this? No, it's not. No, it's not. Anybody here ever push against something to slow it down?
Okay.
Yeah.
Thank you.
So, something is moving this direction and you push backwards on it to slow it down. Is the work here positive or negative? Negative. You're slowing it down. The work is negative. We're going to do a lot of negative work when we talk about things that are slowed down by friction. So if you shove something across a floor and it goes for a little while and then it slows down and stops, negative work was done on it by friction. Okay, and we won't go into a whole lot of depth on this, but I wanted to bring it to your attention that you can have positive and negative work, and the whole Cartesian system that we superimpose on the world plays into it, but also so does whether it is basically being accelerated from rest or slowing down and coming to rest, or just slowing down. Okay, now let's talk about kinetic energy. So, kinetic energy is the energy of an object in motion. You all know this. Right down to the whole kinetic molecular theory and chemistry that we talk about, temperature is objects in motion. Separate thing, we'll set it aside. The other thing to know, and I don't think anybody said this in the what do you know, energy is actually the ability to do work. So energy is something that allows you to exert a force on something and move it. That seems simple enough. If something is moving, it has kinetic energy, that kinetic energy allows it to continue moving. Kinetic energy is the ability of a moving object to apply force and move something. If you have ever been knocked over by something or someone, you have experienced the ability of kinetic energy to do work on you. Whether it's your dog, your sibling, somebody on a basketball court or a volleyball field or on a track or anything else. In one of those really, truly vicious band halftime shows, truly, if you get knocked into and moved, you've just experienced what kinetic energy really means at its root. It's the ability of a moving object to hit something and move it, to exert a force on something and move it. Okay. I hope it's deep. Okay. So, you've got an object. It has a mass. Okay. You know that it's moving when you apply a force to it. We're going to do the whole derivation here. And that gives it an acceleration. So we know that F equals ma, and we know that W equals, and here we get sloppy with this again, F times delta x, or D. We're going to use delta x for a very specific reason here. So we can sub this out and say that work is equal to mass acceleration times, I like mad, work makes me mad. Ha 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 ha. Okay. I know. I have to. But we're going to use Wx again because of the algebra involved. So work is equal to the mass times the acceleration times the distance it moves, the delta x or delta y. Well, if we go all the way back to chapter 2, we have Vf squared equals Vi squared 2a delta x. So we can sub in, well, we can solve for a delta x, which, lo and behold, gives us, so if we're taking this whole chunk and sticking it in here, what we get is that work is equal to mass times Vf squared minus Vi squared divided by 2. What that gets us is that work is equal to 1/2 the mass times the final velocity minus 1/2 mass times the initial velocity. So really, we're just proving here that work and kinetic energy are related. Okay, so we said that energy is the ability to do work. And this, you probably don't remember, again, from physical science. Like I said, most of you seem to have had a fugue state your entire freshman year. That's okay. Kinetic energy is equal to 1/2 the mass of an object times its velocity squared. Kinetic energy is dependent on mass and velocity, but one of those is a whole lot more important. Why? I mean, it's up there. It's written up there which one is. Yeah. Velocity is squared. And I actually want to show you, and I think this is especially poignant because I've got a lot of future engineers in here, but I've also got future pharmacists and future physicians and, I got lots of people who are going to do good stuff, people who are going to design computer systems. Does anybody here remember the Space Shuttle Challenger disaster? You guys would have been elementary?
Yeah.
This was, oh no, sorry, not Challenger, Columbia. Columbia. This is the one that broke up over Texas. This was in 2003, 13 years ago. Maybe you weren't even in school yet. Okay.
I don't remember the event itself, but
Okay, it was, I can tell you, it was a Saturday morning and I had a truck stuck in the mud in the field. I was hauling brush out. I had managed to get a truck stuck in the mud. And I was out there listening to NPR Saturday morning, you know, news radio, and jacking up the truck and putting boards under the wheels. And, oh yeah, they were covering the landing of the shuttle. And at this point, shuttle landings were pretty routine. And I remember hearing them say, well, the shuttle should have been over Florida by now. They should be getting visual confirmation on the shuttle by now. Wait, there are reports coming in from Texas. So what I have is a video clip from a documentary about the disaster. And I would encourage you to go watch the whole thing on your own. It's 53 minutes. It's on YouTube. And it is actually phenomenally compelling television. It's a basically 1 hour documentary, but I want to just watch a piece of it. So we'll go over to that for a moment. The point of that is that velocity is a whole lot more important than mass. And what they find later, spoiler alert here, is that that little 2-pound chunk of foam probably punched a hole right through all of the thermal tiles and left a gaping hole on the leading edge of the wing. So when they re-entered the atmosphere, hot gases seeped right into the wing, broke apart the wing, and then basically were inside the frame of the ship and tore it apart. So, whew.
Was there any way that they could get home safely?
What they talk about a lot, if you continue to watch the documentary, is that the one option would have been to leave them in orbit, take the other shuttle, Atlantis, was actually ready for launch in a week and a half. And one option would have been to take Atlantis up with a smaller than normal crew and transfer the astronauts from Columbia to Atlantis and bring them home on Atlantis. And that basically leave Columbia orbiting and repair it in space later. You know, because by that time they could have spacewalked, they could have assessed the damage, made replacement parts on Earth, and taken them back up. That would have been the only option. There was no safe way to bring that vessel back into the atmosphere,
Because
as is, without repair.
No matter what now, like safety is above all for humans, and even that little piece,
Right.
You wouldn't think they'd look harder into that. Like,
Well, and a lot of the people on the accident board said, you know, you could have done a spacewalk. They take astronauts outside, you know, they do extravehicular activities all the time. I mean, spacewalk is a well-established thing they do. And, you know, why didn't somebody actually physically look at that? Why didn't they get better picture evidence? And I think the engineer at the very beginning, or the administrator, he wasn't an engineer. He was not an engineer. He was an accountant. He was a budget guy. O'Keefe, who was the director at the time, said, you know, when something happens again and again and again and nothing bad results, you start to think, yeah, okay, that's fine. You know, and that's true. I mean, we do that in our everyday lives. Like, hopefully none of, I mean, at this point in my life, and it's been this way, I think most of my adult life, I can't move a vehicle without buckling my seatbelt. Like, it feels weird to me to move a vehicle in a driveway without buckling my seatbelt. But when I was a kid, we didn't always. I mean, my family did, but, you know, lots of people just didn't. Not all cars came with seatbelts when I was a kid. I remember my dad installing seatbelts in our car because it didn't come with backseat seatbelts. You know, so you drive with seatbelts lots of time, nothing bad happens. Yeah, it's fine. You know, of course, we know it's not. We know the physics. It's not. But if something happens again and again and again and nothing goes wrong, feels okay. Right. So it's a human tendency. Okay. So what I want you to look at is problem 5B. This is on page 173. And as I said, I think that you guys could do these in your sleep cold. Because all you're doing is, again, looking at the fact that kinetic energy is equal to 1/2 mass velocity squared. How fast it's moving squared times its mass times 0.5. So in the sample problem 5B, you've got a 7-kilogram bowling ball moving at 3 meters per second. You want to find out how much kinetic energy it has. And then they ask you to compare and look at a much tinier object, a ping pong ball, how fast would the ping pong ball have to be going to have the same kinetic energy? So it's a two-step problem. We'll probably not even get through the first part, but I would ask you to look at it on your own. I am assigning on page 174 numbers 1 through 5. These are the 5B problems. We'll check in on those tomorrow, and I'll have a quick little, it doesn't even seem worth it to do a FIP, but I'll give you a quick little FIP on the 5A. 5B will probably combine with 5C for a FIP. So questions, comments, or concerns?
I'm on the Phoenix box, I think I can post it.
I'll post it. Yeah, you can just take it on your own. So, okay.